welcome to Boring Stuff. Tonight, we'll drift together into the world of quantum physics, a realm where time may bend, reality may split, and logic sometimes takes a quiet step aside. So, settle in, let your thoughts float free, and let's take a slow, peaceful journey through a universe stranger than dreams. One of the most famous and puzzling experiments in quantum physics begins with something that sounds deceptively simple: shining light at a barrier with two narrow openings, known as slits, and watching where the light lands on a screen behind it. At first glance, it appears to be just a basic physics demonstration, the sort of thing that could be set up in a school science lab. But as generations of scientists have discovered, this experiment refuses to behave in a way that matches our everyday understanding of the world. Instead, it reveals something unsettling: that the very act of observation can change reality, and in some cases, it appears that decisions made in the present can influence events that have already happened. In the early 1800s, Thomas Young used this double-slit setup to show that light behaves as a wave. When the light passed through the two slits, it spread out and overlapped, creating a pattern of alternating bright and dark bands on the screen. This interference pattern could only be explained if light was behaving like a wave, with peaks and troughs combining or canceling each other out. If light had been made up of particles that traveled in straight lines, the result would have been two bright stripes directly behind the slits, not the complex set of fringes that actually appeared. But in the early 20th century, the picture became more complicated. Quantum theory revealed that light can also behave like a particle, in the form of photons, discrete packets of energy. When scientists performed the double-slit experiment using single photons, firing them one at a time, they expected that each particle would travel through one slit or the other and gradually form two bands on the screen. Instead, even when photons were sent individually, the interference pattern still emerged over time, as if each photon somehow passed through both slits simultaneously and interfered with itself. This was the first great puzzle. It seemed as though reality refused to decide whether light was a wave or a particle until it was measured. And if the experimenter set up a detector to see which slit the photon went through, the interference pattern disappeared entirely. The photons behaved like particles going through one slit or the other, not both. The delayed choice experiment, first proposed by the American physicist John Archibald Wheeler in the 1970s, took this strangeness a step further. Wheeler asked, what if we decided whether or not to measure the photon's path after it had already passed through the slits? Could the photon somehow know in advance what we were going to do? In the delayed choice version of the experiment, the setup includes a device that can switch between detecting the path and not detecting it, with the choice made only after the photon has passed through the slits but before it hits the screen. When the experiment is run, the result is astonishing. If the choice is made to detect the photon's path, the interference pattern disappears, even though the photon has already gone through the slits. If the choice is made not to detect the path, the interference pattern appears. It is as if the photon's past behavior, whether it traveled as a wave or a particle, is determined retroactively by a decision made in the present. But the delayed choice quantum eraser, first carried out in the 1990s by physicists Yoon-Ho Kim and colleagues, pushed the paradox further still. In this experiment, pairs of photons are created simultaneously. One photon, called the signal photon, heads toward the screen to form an interference pattern. The other, called the idler photon, is sent on a much longer, more complicated journey through a set of detectors. By measuring the idler photon in specific ways, scientists can either preserve or erase information about which slit its partner went through. Here is where the strangeness deepens. The measurement of the idler photon is made after the signal photon has already hit the screen. And yet, when researchers look at the results, they find that if the witch path information is preserved, no interference pattern appears in the data from the signal photon. If the witch path information is erased, the interference pattern appears, even though the decision to preserve or erase that information was made after the signal photon had already been recorded. It is tempting to say that the future is somehow reaching back to change the past, but physicists are careful in how they interpret this. Most agree that no actual signal is traveling backward in time. Instead, the phenomenon reveals the deep interconnectedness of quantum events, where the concepts of before and after lose their conventional meaning. The past and future are linked in ways that defy classical intuition. In ordinary life, cause precedes effect. You flip a switch, and the light turns on. You push a ball, and it rolls across the floor. These relationships are so ingrained in our thinking that it is difficult to imagine a world in which the order can blur. But in the quantum world, measurements do not simply reveal what is already there. They play a role in shaping the outcome. The delayed choice quantum eraser shows that in certain experiments, the context of the measurement, including actions taken after an event, can determine how that event is recorded. Some physicists frame this in terms of the wave function, a mathematical object that encodes all the possible states a quantum system could be in. Until a measurement is made, the system is described by a superposition of possibilities. The act of measurement selects one outcome from that range. In the quantum eraser setup, the final measurement on the idler photon changes how we must describe the history of the signal photon. The interference pattern, or lack of it, is not a matter of altering the past, but of choosing a consistent story that fits the measurements taken across the entire system. Others see it as a lesson in humility about the limits of our classical language. Terms like, the photon went through this slit, or the photon behaved like a particle, may be misleading when applied to quantum events. In the delayed choice quantum eraser, it is not that the photon changed what it did in the past, but that its behavior cannot be fully described without taking into account the entire experimental arrangement. Even parts that are set up after the photon's journey seems to be over. The implications are unsettling but also profound. If the outcome of a quantum event depends on future conditions, then the flow of time in the quantum world may be less like a one-way street and more like a web, with connections looping in ways that our everyday experience cannot prepare us for. While these effects cannot be used to send messages into the past or alter history in the way science fiction often imagines, they hint that reality itself may not be bound to a single, unchanging timeline. In the end, the delayed choice quantum eraser is not just a technical curiosity. It is a reminder that at the smallest scales, nature does not fit neatly into the categories we use to describe it. Our common sense ideas about cause and effect, past and future, and the independence of events all have to be reconsidered. This is the quiet, patient work of physics, to let the experiments guide our understanding, even when they lead us into territory that seems to defy reason. In quantum physics, the question, what is real, is not as straightforward as it seems. In everyday life, reality appears to be fixed and shared. If two people are looking at the same clock, they will agree on what time it shows. If they watch a coin flip, they will both see it land heads or tails. There might be disagreements about interpretations or opinions, but the basic facts of what happened remain consistent. The thought experiment known as Wigner's friend challenges this comfortable assumption by showing that, at least in the quantum realm, two observers can experience different realities, and both can be correct from their own point of view. The scenario begins with a physicist, Eugene Wigner, imagining a laboratory where an experiment is being run on a single quantum particle. For instance, measuring the spin of an electron or the polarization of a photon. Inside the lab is Wigner's friend, who will make the measurement and record the result. From the friend's perspective, the moment they measure the particle, its quantum state collapses into a definite value: spin up or spin down, polarization horizontal or vertical. The friend writes this outcome in their notebook. Inside the lab, there is no uncertainty. The result is real and settled. But now, consider Wigner's perspective, standing outside the closed laboratory. If the lab is completely isolated from the outside world, Wigner has no way of knowing which result the friend obtained. According to quantum theory, before Wigner opens the door and interacts with the lab, the entire system, the particle, the measuring device, and even the friend's mind, must be described as a superposition of all possible outcomes. From Wigner's standpoint, the friend is in a state of having seen both results at once, entangled with the particle. This is where the strangeness emerges. Inside the lab, the friend experiences a definite reality. Outside the lab, Wigner describes that same situation as a blurred mixture of possibilities. Both descriptions are consistent with the rules of quantum mechanics, yet they do not match in any intuitive sense. If reality were a fixed set of facts, there should not be two incompatible but correct accounts of the same event. The Wigner's friend thought experiment was introduced in 1961, decades before physicists had the technology to seriously test it. At the time, it was meant as a philosophical probe, highlighting the peculiar role of measurement in quantum theory. In classical physics, measurements reveal properties that objects already have. In quantum mechanics, measurements seem to create those properties, but only from the point of view of the observer who performs the measurement. For someone who has not yet interacted with the system, the possibilities remain open. In recent years, versions of the Wigner's friend experiment have been implemented in laboratories using entangled photons and other systems small enough to be manipulated according to quantum rules. In 2019, a team of researchers reported results that suggested different observers could indeed record and verify different realities without contradiction. While the experiments are still limited in scope and subject to debate about interpretation, they have revived interest in the question: is reality something that exists independently, or is it tied to the perspective of each observer? There are several ways to make sense of the paradox, depending on how one interprets quantum mechanics. In the Copenhagen interpretation, measurement is an action that updates the observer's knowledge, and there is no absolute description of the system that works for all observers at once. In this view, the friend's measurement inside the lab produces a definite outcome for them, but until Wigner interacts with the lab, his description must include all possibilities. In the many worlds interpretation, there is no collapse at all. Instead, when the friend measures the particle, the universe splits into branches, one where the friend sees result A, and another where the friend sees result B. From Wigner's perspective, both branches still exist, and he is entangled with them until he opens the lab and becomes part of one branch himself. In this interpretation, the two realities are not just perspectives, but parallel histories that coexist without influencing each other. Another approach, called relational quantum mechanics, suggests that facts are not absolute but relational. They exist only in the context of an interaction between systems. The friend's measurement produces a fact relative to the friend. Wigner's description is a fact relative to Wigner. Neither is more fundamental, and there is no single, global reality that contains all facts at once. Regardless of the interpretation, the key message of the Wigner's friend scenario is that in quantum mechanics, reality may not be a single, observer-independent structure. It may be more like a network of interlinked perspectives, each consistent within itself but not necessarily reconcilable into a single picture. This is deeply at odds with the way we experience the world at human scales, where shared facts form the basis of communication, science, and society. To understand why the quantum world can sustain such differences, it helps to recall that quantum states are not physical objects in the classical sense, but mathematical tools for predicting the outcomes of measurements. When the friend measures the particle, they update the quantum state according to the result. When Wigner describes the entire closed lab, he uses a quantum state that includes all possible results. Both descriptions are valid in their own right because they apply to different systems and different sets of information. The challenge comes when we try to merge these viewpoints. In everyday life, if two people disagree about a fact, we can in principle compare notes and find out who is correct. In the Wigner's friend setup, both can be correct within their own frame of reference, yet their accounts cannot be combined without contradiction. If quantum mechanics applies universally, even to conscious observers, then there is no guarantee that a single, unified account of reality exists. This conclusion is uncomfortable for many physicists, because the scientific method relies on the idea that experiments produce objective results that anyone can verify. If results can be observer-dependent in a fundamental way, then our picture of science as a quest for a single, shared truth might need to be adjusted, at least when dealing with the quantum domain. It is important to note that in most practical situations, the differences between observers vanish almost instantly. Quantum superpositions tend to collapse, or decohere, when they interact with their environment, making the outcomes effectively objective. That is why we do not see everyday objects in multiple states at once. The Wigner's friend paradox becomes relevant only in highly controlled conditions, where quantum systems are carefully shielded from outside influences. Still, the thought experiment raises questions that reach beyond physics into philosophy. If reality depends on the observer, what does that say about the nature of truth? Is the world something out there that exists independently of us, or is it, at least in part, constructed by our observations? And if different observers can have equally valid but conflicting accounts, how do we decide what counts as reality? The Wigner's friend scenario does not provide final answers, but it offers a clear warning. Our everyday intuitions about reality are not guaranteed to hold at the quantum level. The framework that works so well for describing planets, buildings, and people may not be adequate for describing electrons, photons, and other microscopic entities. At the smallest scales, reality may be richer, stranger, and more fragmented than we imagine. A tapestry woven not from a single thread but from many, each seen from a different vantage point. Hardy's paradox is one of those quantum puzzles that looks, at first glance, like it must be a trick or a misinterpretation. It seems to suggest that something can interfere with nothing, that a particle can leave a mark without ever having been in the place where the mark was made, and that logic, as we usually apply it, fails to explain what is going on. It is not as famous as the double-slit experiment or Schrödinger's cat, but for those who study quantum mechanics, it is a deeply unsettling reminder that the quantum world refuses to obey the rules we use in everyday life. The paradox, first described by physicist Lucian Hardy in 1992, involves two particles such as an electron and a positron. A positron is the antimatter counterpart of an electron. It has the same mass but the opposite electric charge. In our story, the particles are prepared in such a way that their paths can overlap in a specific region of space. If both the electron and the positron are in that same region at the same time, they will annihilate each other, turning into a burst of energy, typically in the form of gamma-ray photons. This is not just a theoretical detail. It is a well-established fact of particle physics. To set up Hardy's thought experiment, imagine two separate interferometers. These are devices that split a particle's path into two possible routes, then bring them back together so that the two paths can interfere, creating patterns that depend on how the paths were combined. One interferometer is for the electron, and the other is for the positron. The paths of the two devices are arranged so that one path from each interferometer passes through the same point in space, the point where the two particles would meet and annihilate if they were both there at the same time. The clever part of the setup is that the interferometers are tuned so that, under normal circumstances, a particle entering them will always be detected in a particular output port. Call it the bright port, and never in the other dark port. This is because of the way interference works. The two possible paths a particle could take combine in such a way that they cancel out in the dark port and reinforce in the bright port. If nothing disturbs the system, this is guaranteed. Now, consider what happens if the electron and positron are sent into their respective interferometers at the same time. If they both take the overlapping path, they will annihilate, and neither will be detected at the output. But if one particle takes the overlapping path and the other does not, there is no annihilation, but the interference pattern is disturbed for the particle that encountered the empty overlapping path. This disturbance means that the particle has a chance of being detected in the dark port instead of the bright one. Here is where the paradox emerges. Occasionally, when the experiment is run, both the electron and the positron are detected in their respective dark ports. The only way for a particle to end up in the dark port is if its interference was disturbed, which, in this setup, can only happen if the other particle took the overlapping path. So, if the electron is in the dark port, it must be because the positron took the overlapping path, and if the positron is in the dark port, it must be because the electron took the overlapping path. But if both took the overlapping path, they should have annihilated, leaving no particles to detect at all. This is the contradiction at the heart of Hardy's paradox. The results suggest that each particle knew the other was in the overlapping path, even though they could not both have been there without annihilating. It is as if the particles interacted with the possibility of the other's presence, not with the actual presence. The effect is detectable, even in situations where one might say nothing was there. Hence the idea of something interfering with nothing. Physicists have tested versions of Hardy's paradox in the laboratory using photons instead of electrons and positrons, because photons are easier to manipulate and detect without disturbing them too much. In these optical experiments, the logic is the same. The presence or absence of interference reveals information about the possible path of another particle. The results match Hardy's predictions, confirming that the paradox is a genuine feature of quantum mechanics, not a mathematical trick. One way to think about this is to remember that in quantum mechanics, particles do not have definite paths until they are measured. Instead, they exist in a superposition of all allowed paths, each with its own probability amplitude. when two particles' possible paths overlap, even if they are not actually there at the same time. In the classical sense, the superpositions can still interact. In Hardy's setup, the particles carry information about the possibilities they could have taken, and this information can alter the interference patterns in ways that mimic an actual interaction. This challenges our classical intuition in two important ways. First, it suggests that the absence of a particle is not the same as nothing at all. The possibility of a particle being in a certain place can have physical consequences, even if the particle is ultimately detected somewhere else. Second, it shows that quantum systems can encode information about what would have happened under circumstances that did not actually occur in the same run of the experiment. Interpreting Hardy's paradox depends, as always in quantum mechanics, on one's preferred philosophical stance. In the Copenhagen interpretation, the paradox reflects the fact that quantum states are probability tools, not literal descriptions of particle paths. The disturbance in the interference pattern is a result of the change in possible histories, not an actual collision between particles. In the many worlds interpretation, one might say that in one branch of the universe, the particles did meet and annihilate, while in another branch they did not, and the interference patterns in each branch reflect those different histories. There is also a connection to the idea of counterfactual reasoning, asking, what would have happened if? Hardy's paradox seems to give physical meaning to such counterfactuals in the quantum world. The particles behave as if they know about events that could have happened but did not, and they leave measurable traces of those unrealized events. This is profoundly different from classical physics, where unrealized possibilities have no effect on the actual outcome. The paradox also hints at the broader principle that quantum mechanics is not about particles moving along well-defined paths, but about the relationships between different possible states. In Hardy's experiment, the overlapping paths matter not because the particles travel them in the classical sense, but because those paths are part of the network of possibilities that define the entire system. The strange results are a consequence of the way those possibilities interfere with each other. In the end, Hardy's paradox is another reminder that the quantum world is governed not by the logic of everyday objects, but by the mathematics of probability amplitudes. In this domain, something can leave a mark without being present in the ordinary sense, and nothing can be just as real in its effects as something. The experiment does not violate the laws of physics. It follows them exactly, but it shows that those laws operate on principles that are far removed from common sense. The pigeonhole principle is one of the simplest and most intuitive ideas in mathematics and logic. It states that if you have 3 pigeons and only 2 pigeonholes, then at least one pigeonhole must contain more than one pigeon. The principle is so basic that it feels almost beyond questioning. It is not a matter of probability or guesswork. It is a certainty that follows directly from counting. If you try to arrange 3 objects into 2 boxes, duplication is unavoidable. In the quantum world, however, this straightforward logic can be violated in a way that seems impossible. The so-called quantum pigeonhole principle shows that under certain experimental conditions, 3 particles can be placed into 2 boxes in such a way that no 2 particles are ever found in the same box. This does not mean the particles have been hidden in extra boxes or spread across space in ways we did not account for. Rather, it means that our classical assumptions about how particles occupy positions break down when quantum rules take over. The basic version of the quantum pigeonhole effect was proposed by Yakir Aharonov and colleagues in 2014. To understand it, imagine you have 3 electrons and 2 boxes, which we will simply call box A and box B. In the classical world, if you place each electron into one of these boxes and then check where they are, you must find that at least 2 electrons are in the same box. The principle is as solid as basic arithmetic. The quantum twist begins when we prepare each electron not in a definite state of being in box A or box B, but in a superposition of both states at once. This means that, until measured, each electron is not located in a single box, but exists in a state that combines in box A and in box B simultaneously. We can write this mathematically, but the key point is that the electrons are not committed to a single location until we make a measurement. Now, in the quantum pigeonhole scenario, the experiment is arranged so that we do not measure directly which box each electron is in at the start. Instead, we prepare them in these superposition states, and then, at the end of the process, we perform what is called a post-selection, a measurement that keeps only certain outcomes. The post-selection is designed to ensure that, when we later examine correlations between the particles, no 2 electrons ever appear in the same box, even though there are only 2 boxes and 3 electrons. This is the core of the puzzle. If we were to measure all the electrons directly at the start, we would always find at least 2 in the same box, as the classical pigeonhole principle dictates. But by structuring the experiment so that we only consider cases that pass a specific final measurement condition, the results show that each pair of electrons behaves as if they were never in the same box at the same time. Even when we look at all 3 electrons, the data suggests no pair ever shared a box. This seems to defy the classical counting argument. One way to see what is happening is to recognize that in quantum mechanics, properties like being in box A or being in box B are not always definite before measurement. Instead, the electrons can be described by probability amplitudes that can interfere with each other. When certain post-selection conditions are applied, these amplitudes can combine in such a way that the configurations where 2 electrons share a box are effectively eliminated from the set of outcomes we see. The effect is not achieved by physically moving electrons around, but by the mathematical structure of quantum states and how measurements filter them. This highlights a key difference between classical and quantum reasoning. In the classical pigeonhole principle, the location of each object is a definite fact, whether or not we know it. In the quantum version, the location is not a definite fact until measured, and the act of measuring, especially with carefully chosen initial and final conditions, can reveal patterns that seem impossible from a classical standpoint. In this case, the pattern is that no 2 particles share the same box, even though there are more particles than boxes. The quantum pigeonhole effect is not just a curiosity for thought experiments. It connects to deeper principles in quantum mechanics, such as entanglement and contextuality. Entanglement refers to the way quantum particles can share correlations that have no classical counterpart, while contextuality refers to the idea that the outcome of a measurement can depend on the set of other measurements being performed. In the pigeonhole scenario, the way we choose to measure the system and the conditions we apply to select the final results change the relationships between the particles in a way that has no analog in classical physics. Some physicists have pointed out that the effect also challenges our intuitive sense of where a particle is at any given moment. If the electrons in the experiment behave as if they never share a box, then our usual mental picture of particles as small billiard balls with definite positions may be misleading. Instead, the electrons are part of a global quantum state that only produces definite, classical-like facts when measured. Between those measurements, their locations may not be meaningful in the way we are accustomed to thinking about them. Others emphasize that the quantum pigeonhole principle does not truly break mathematics. It does not contradict the classical pigeonhole principle, because the latter assumes objects have definite, independent positions at all times. The quantum version suspends that assumption. Once you allow for superposition and the strange filtering effects of post-selection, the violation becomes a reflection of how different the quantum world is from the classical one, rather than a breakdown of logic itself. In experiments that test this idea with photons, researchers create optical setups that mimic the two boxes using different paths the photons can take. By preparing the photons in superposition states and carefully arranging the measurements at the end, they can demonstrate correlations that show no two photons are ever in the same path, even when there are more photons than paths. The results match the predictions of the quantum pigeonhole principle, confirming that this is not just a mathematical trick, but a real, measurable feature of quantum systems. The broader implication of the effect is that quantum systems can avoid constraints that are absolute in the classical world, simply by existing in a superposition of possibilities and by being filtered through specific measurement conditions. This is not a loophole or a violation in the sense of breaking a law. It is a demonstration that the laws we think of as universal are actually limited to a particular framework, the framework of classical definite states. In quantum mechanics, where states can be indefinite and interconnected until the moment of measurement, those constraints no longer apply in the same way. For students of quantum theory, the quantum pigeonhole principle is both fascinating and humbling. It shows that even the simplest and most obvious truths from everyday reasoning, the kinds of truths that seem beyond question, can fail when we enter the quantum domain. It forces us to accept that quantum particles are not little classical objects that happen to be very small. They are fundamentally different entities, obeying a set of rules that only occasionally align with our macroscopic intuition. The three-box paradox is another of those thought experiments in quantum mechanics that begins with something familiar and ends in a place that feels almost contradictory. It starts with the idea that if you have a particle and you place it in one of three boxes, you can, with enough careful checking, figure out which box it is in. This seems obvious, and in the classical world it is. But in quantum mechanics, the situation can be arranged so that measurements give you results that appear to be too certain. In fact, the results can suggest that the same particle is in more than one box, depending on how you look at it, which should be impossible under ordinary reasoning. The paradox, proposed by Yakir Aharonov and Lev Weidman in the early 1990s, uses a concept called preselection and post-selection. Preselection means preparing a particle in a specific initial quantum state before you begin the experiment. Post-selection means measuring the particle at the end and keeping only the results where the final measurement shows a specific outcome. When these two conditions are combined, something unusual can happen in between, in the time after the preselection and before the post-selection, that allows for surprising conclusions about where the particle was in the middle. To set up the three-box paradox, imagine you have a single particle prepared in such a way that, before any measurements are made, it is equally likely to be in box 1, box 2, or box 3. In quantum terms, this means the particle is in a superposition of the three locations. The wave function describing the particle contains equal contributions from each box, and until you measure, you cannot say it is in any one box in particular. The twist comes from the post-selection. At the end of the experiment, you make a final measurement that selects only those particles that end up in a very specific state, one that is also a superposition of being in all three boxes, but with certain differences in the relative phases of those states. This final measurement effectively filters the results, keeping only those runs of the experiment where the particle fits this chosen ending state. The paradox arises when you consider what would happen if, halfway between the preparation and the final measurement, you decided to open one of the boxes to check whether the particle was there. According to the predictions of quantum mechanics, if you open box 1 in the middle of the experiment, you will find the particle there with 100% certainty. In every single run of the experiment that survives the post-selection. This alone is surprising, since the initial preparation suggested the particle had only a 1 in 3 chance of being in that box. But the surprise deepens when you consider what happens if, instead of opening box 1, you open box 2. In that case, the same logic applies. You will find the particle there with 100% certainty as well, again in every run that makes it through to the post-selected final state. This is the core of the paradox. It seems as though the particle is definitely in box 1 if you look there, and definitely in box 2 if you look there instead. But these cannot both be true in the classical sense, because the particle is only in one place at a time in classical physics. In the quantum version, the rules are different. The combination of the initial preparation, the special post-selection, and the rules for how quantum measurements affect superpositions means that each of these statements is correct within its own context, but they cannot be combined into a single, consistent picture of the particle's location. The paradox becomes clearer when you remember that quantum mechanics is not describing a particle moving around like a tiny billiard ball. Instead, it is describing the evolution of a wave function, which encodes all the possible states of the particle and how they interfere with one another. When you open a box and look inside, you are performing a measurement that changes the wave function, collapsing it into a state consistent with the outcome you see. In the three-box paradox, the collapse triggered by looking in box 1 leads to the result that the particle is there with certainty. But if you had chosen instead to open box 2, the collapse would have led to the particle being there with certainty. The fact that these statements cannot be combined into a single narrative reflects a deeper truth about quantum mechanics. It is a theory about what you can say regarding the outcomes of measurements, not necessarily about what is really happening in between those measurements. If you try to imagine that the particle has a definite position at all times, you will quickly run into contradictions in cases like the three-box paradox. Some interpretations of quantum mechanics handle this paradox more comfortably than others. In the Copenhagen interpretation, the particle simply does not have a definite location before you measure it, so there is no contradiction in saying that it is certain to be in one place, given one measurement choice, and certain to be in another place given a different choice. The many worlds interpretation resolves the paradox by saying that each measurement choice branches the universe, and in one branch you find the particle in box 1, while in another branch you find it in box 2. Both are real outcomes, but they occur in different branches that cannot interact. The paradox also connects to the concept of weak measurements, which allow experimenters to gather limited information about a quantum system without fully collapsing the wave function. In weak measurement studies of the three-box setup, researchers have found results that match the idea that the particle has a measurable presence in more than one box at the same time. These results do not mean the particle is literally divided like a piece of clay. Rather, they reflect the strange, non-classical distribution of probability amplitudes in the quantum state. The broader lesson of the three-box paradox is that certainty in quantum mechanics can be context-dependent. In the classical world, if something is certain in one context and certain in another, both certainties should be compatible. In the quantum world, this is not always the case. The combination of pre-selection and post-selection can create situations where the middle of the experiment is constrained in ways that produce seemingly impossible certainties. This has implications beyond simple thought experiments. In quantum information theory, for example, similar effects can influence how information is stored, transferred, and erased in quantum systems. Understanding how pre- and post-selection shape the possible histories of a quantum system can be important for designing quantum algorithms and error correction methods. It also plays a role in certain interpretations of time in quantum mechanics, where the past and future can jointly influence the probabilities of present events. For those encountering the three-box paradox for the first time, it can feel like a cheat, as though the experimenters have set up a trick with the measurements to create an illusion. But it is not an illusion. It is a direct consequence of the formalism of quantum mechanics. The rules that govern how superpositions evolve and how measurements collapse them are precisely what allow such impossible certainties to arise. The paradox is not a flaw in the theory, it is a window into how the theory works. The quantum Cheshire Cat is named after the fictional cat in Lewis Carroll's Alice's Adventures in Wonderland, famous for disappearing entirely while leaving its grin floating in the air. The quantum version of this idea is not just a whimsical metaphor. It describes a real physical effect in which a particle and one of its measurable properties appear to be separated, as if the smile of the particle exists in a different place than the particle itself. While no actual cat is involved, the result challenges one of our most basic intuitions about the world, that an object and its properties are inseparable. To understand this effect, we need to think about how quantum mechanics treats particles and their attributes. In classical physics, a particle is a small object with a set of definite properties, such as position, momentum, and spin. These properties are attached to the particle at all times. You cannot meaningfully talk about the position of a particle without the particle being there. In the quantum world, however, properties can be in superposition, just like the particle's position can be. This opens the door to the possibility that the location of a property could, under certain measurement conditions, differ from the location of the particle itself. The first experimental demonstration of the quantum Cheshire Cat effect was carried out in 2014 using neutrons. Neutrons are subatomic particles found in atomic nuclei, and they possess a property called spin, which can be thought of, very loosely, as a kind of intrinsic angular momentum. In the experiment, a beam of neutrons was sent through a device known as an interferometer, which split the beam into two distinct paths and then recombined them. This setup is similar in spirit to the double-slit experiment, but adapted for particles with spin. Before the neutrons entered the interferometer, they were prepared in a particular quantum state that was a superposition of being in both paths with different spin orientations. Once inside, the two paths could be manipulated separately. One path could be modified in a way that interacted with the neutron's position, while the other path could be modified in a way that interacted with their spin. At the end of the interferometer, the paths were brought back together, and a final measurement was made that only selected neutrons in a certain combined state of position and spin. This is the post-selection step, familiar from earlier paradoxes we have discussed. When the researchers analyzed the results, they found something striking. The neutrons themselves, as particles, seemed to travel predominantly along one path through the interferometer, while their spin property behaved as if it had traveled along the other path. In other words, the measurements suggested that the particle was in one place, but one of its attributes was in a different place entirely. This is the essence of the quantum Cheshire cat, the apparent separation of a particle from one of its properties. It is important to be clear about what this means. The experiment does not show that the spin literally floats away from the neutron like the Cheshire cat's grin from its face. Instead, it shows that the outcomes of certain measurements can be interpreted as if the property and the particle were in different places. This interpretation comes from the formalism of quantum mechanics, particularly when using weak measurements. Weak measurements allow scientists to probe a system in a way that disturbs it only slightly, revealing statistical patterns without collapsing the quantum state completely. When combined with post-selection, weak measurements can yield results that seem to contradict our classical ideas about how particles and properties are connected. From a classical point of view, the quantum Cheshire cat is puzzling, because we think of properties as belonging to objects in an inseparable way. You cannot meaningfully talk about a car's speed without the car itself being present. You cannot measure the temperature of an ice cube without having the ice cube there. In quantum mechanics, however, properties like spin or polarization are not fixed labels attached to particles. They are aspects of the wave function, which can be distributed across space in ways that do not match the location of the particle's mass or charge. The effect has also been demonstrated with photons, using their polarization, the orientation of the electromagnetic wave, as the property of interest. In these optical experiments, the photon's position and its polarization can be manipulated independently in different arms of an interferometer. By carefully choosing the pre- and post-selected states, researchers can produce results in which the photon appears to travel one route while its polarization is detected in another. The analogy to the Cheshire cat's grin is even stronger here, since the polarization can be thought of as a feature of the photon in the same way a grin is a feature of a cat. The quantum Cheshire cat effect is more than just a curiosity. It has practical implications for precision measurements. If a property can be effectively separated from the bulk of a particle's interaction with its environment, it might be possible to measure that property more accurately, with less interference from other factors. For example, in neutron experiments, separating the spin from the neutron's main path could allow for more sensitive tests of how spin interacts with external fields. Similarly, in optical systems, separating polarization from the main path of photons could be useful in metrology and quantum information processing. Interpreting the effect depends on one's philosophical stance toward quantum mechanics. In the standard interpretation, the separation is not a literal movement of properties away from particles, but a result of how the wave function is distributed and how measurements are chosen. The wave function can have different components in different locations, and measurements can pick out these components in ways that suggest separation. In the many worlds view, the measurement outcomes correspond to different branches in which the particle's property is detected in different contexts, but the overall quantum state still contains all possibilities together. Some researchers argue that the quantum Cheshire cat is not so much about separation as it is about the contextual nature of quantum properties. In this view, the property exists only in relation to the measurement that reveals it. If the measurement is designed to reveal spin in one path, then that is where the spin is said to be. If the measurement is designed to reveal position in another path, that is where the particle is said to be. The separation is then a feature of how we are interrogating the system, not a physical splitting of the particle from its property. Nevertheless, the effect challenges our mental models. It shows that the intuitive link between an object and its characteristics is not absolute in the quantum world. A particle's position and its other attributes can be associated with different spatial regions, depending on how the system is prepared and measured. This flexibility is not something we encounter in our macroscopic experience, which is why it feels so strange. The quantum Cheshire cat serves as another reminder that quantum mechanics operates on a different logic from the everyday world. In the realm of the very small, even the most basic assumptions, such as an object and its properties are always together, can be overturned by careful experiments. By studying these effects, physicists not only deepen their understanding of quantum theory, but also develop tools and techniques that might one day lead to new technologies. One of the strangest lessons of quantum mechanics is that sometimes you can find out that something is there without ever interacting with it in the usual way. In our everyday experience, detection involves some form of contact. Light reflects off an object and reaches our eyes, or a sensor absorbs energy from whatever it is measuring. If you want to check whether an object is present, you expect to disturb it at least slightly in the process. The Elitzur-Weidmann bomb tester, proposed in 1993 by Avshalom Elitzur and Lev Weidmann, turns that assumption on its head. It shows that quantum mechanics allows for a type of interaction-free measurement, in which you can detect the presence of something without directly touching it at all. To understand the problem they posed, imagine a warehouse filled with extremely sensitive bombs. These are not just ordinary explosives. They are so delicate that even a single photon, a particle of light, striking the trigger mechanism will cause them to explode. Some of the bombs are real and functional, but some are defective and will never explode no matter what. The challenge is to find out which bombs are real without setting them off. In a classical world, this would be impossible. The only way to test a bomb would be to interact with it in a way that would cause it to explode if it were real. The key to solving this puzzle lies in the quantum phenomenon of superposition and interference. Elitzur and Weidmann imagined using a Mach-Zehnder interferometer, a device that splits a photon's path into two routes and then recombines them. Under normal circumstances, the two paths are arranged so that they interfere with each other perfectly, producing a predictable outcome. The photon always ends up at one detector and never at the other. This interference pattern depends on the fact that both paths are open and undisturbed. Now, suppose we place one of the bombs in one of the two paths of the interferometer. If the bomb is a dud, the photon can pass through that path just as before, and the interference pattern will remain intact. But if the bomb is real, the path containing it is effectively blocked. The photon cannot pass through without triggering the bomb. Here is where quantum mechanics provides a surprising advantage. Because the photon was in a superposition of taking both paths, the removal of one path's contribution to the interference pattern changes the possible outcomes. If the bomb is real, there is now a chance that the photon will end up at the detector that would never have clicked in the undisturbed case. When that happens, we can conclude that the bomb must be real, because the only way to produce this outcome is if the interference was disturbed by the blocked path. And, crucially, in these cases, the photon must have taken the other path entirely, never touching the bomb at all. We have learned that the bomb is functional without triggering it. This is the essence of an interaction-free measurement. The bomb's presence changes the interference pattern, and by observing that change, we gain information about the bomb without having to directly interact with it in a way that transfers energy or triggers an explosion. The photon's potential to take both paths allows it to be influenced by the possibility of the bomb's presence, even when it actually takes the safe path. The process is not perfect. In some trials, the photon will take the path with the real bomb and cause it to explode, giving us the same information in a destructive way. In other trials, the photon will take the safe path but end up at the normal detector, leaving us with no information about the bomb. However, in a significant fraction of cases, the photon will arrive at the impossible detector, telling us that the bomb is real without ever touching it. By running many photons through the setup, we can identify a large portion of the real bombs without detonating them. Later, refinements of the idea improved its efficiency. By using more complex setups with multiple beam splitters and mirrors, the probability of detecting a real bomb without exploding it can be made arbitrarily close to 100%. These schemes rely on the so-called quantum Zeno effect, the phenomenon where frequent measurements can effectively freeze the evolution of a quantum state. In the bomb tester context, this means repeatedly checking whether the photon is heading toward the bomb in such a way that, if the bomb is real, the photon almost always chooses a safe path without triggering it. The Elitzer-Weidmann bomb tester is more than a clever story about explosives. It demonstrates a fundamental point about quantum physics, that the set of possible outcomes in an experiment can be changed by the mere possibility of an interaction, even if the interaction never occurs. The photon's behavior is altered by the existence of a path it could have taken, and the blocking of that path leaves an observable trace in the interference pattern. This effect has practical applications beyond bomb detection. In quantum imaging, for example, interaction-free measurement techniques can be used to form an image of an object without exposing it directly to damaging radiation. This could be valuable for imaging delicate biological samples or fragile materials. Similarly, in quantum computing and communication, interaction-free principles might help detect the presence of eavesdroppers or other disturbances without directly revealing information to them. From a philosophical standpoint, the bomb tester challenges our understanding of causality and information. How can we learn about the existence of something without interacting with it? The answer lies in the fact that in quantum mechanics, interaction can include the disturbance of interference between possible paths. The presence of the bomb changes the set of possible histories for the photon, and by detecting the difference in those histories, we gain knowledge without direct contact. Some interpretations of quantum mechanics frame this in terms of the wave function extending along both paths. In the standard view, the photon is described by a wave function that includes contributions from both the bomb path and the safe path. When the bomb blocks one path, it changes the wave function structure, and this change is visible in the outcomes. In the many worlds interpretation, the situation can be seen as branching. In one branch, the photon takes the bomb path and causes an explosion, while in another branch it takes the safe path. The cases we see as interaction-free are simply those where we find ourselves in the safe branch. The Elitzer-Weidmann bomb tester is another reminder that in the quantum world, possibilities can have as much influence as actual events. The blocked path that the photon does not take is just as important in shaping the outcome as the path it does take. This is far removed from classical thinking, where only actual interactions can change results. In quantum mechanics, the counterfactual, what could have happened but did not, can leave a measurable mark on reality. One of the most surprising features of quantum mechanics is the existence of correlations between particles that cannot be explained by any local classical theory. Most people have heard about entanglement, where two particles share a joint quantum state so that measuring one instantly reveals information about the other, no matter how far apart they are. These spooky actions at a distance, as Einstein once called them, are now a well-studied and experimentally confirmed part of physics. But there's another, less widely known phenomenon that is equally puzzling in its own way: quantum non-locality without entanglement. This is a discovery that certain types of quantum correlations that seem to require some kind of shared link, can appear even when there is no entanglement between the particles at all. At first, this sounds contradictory. Entanglement is generally considered the main source of non-locality in quantum mechanics. Without entanglement, one might expect that particles behave independently, and that their measurement results can be explained by classical probability rules. Yet, in 1999, researchers Sandu Popescu and Daniel Rohrlich pointed out a class of situations in which unentangled particles can still display correlations that defy classical explanation. These correlations are weaker than those produced by entangled particles, but they are nonetheless beyond what would be expected from any local hidden variable model. To understand this, it helps to remember that quantum mechanics deals with probability amplitudes, not just probabilities. Even when two particles are not entangled, the way their individual states are prepared and measured can produce statistical outcomes that cannot be reproduced by a simple combination of independent probabilities. This is because the measurement settings, the choice of basis, and the quantum nature of the particles themselves allow for interference effects that do not require entanglement but still produce correlations that classical systems cannot mimic. Consider two particles prepared in certain mixed states that are not entangled. If each particle is measured separately in a particular way, the joint outcomes might still show correlations that violate what is known as a Bell-type inequality, a mathematical condition that must hold for any theory based purely on local realism. Normally, the violation of such inequalities is taken as a signature of entanglement. But here, the violation emerges from subtler quantum effects related to the structure of the states and measurements, not from the presence of entanglement itself. One way to picture this is to imagine two musicians playing in different rooms. They are not communicating, and they did not rehearse together in a way that perfectly locks their performances into a shared rhythm, which would be the analogy for entanglement. Yet, somehow, when you listen to both recordings later, you find patterns that line up more often than they should if the music was purely independent. The musicians are not in sync in the classical sense, but the rules governing how they play, in this analogy, the quantum rules, create unexpected alignments that would be hard to explain by coincidence alone. Experimental demonstrations of quantum non-locality without entanglement often involve photons. In some setups, two photons are created independently and given certain polarizations. These photons are then sent to different detectors, where their polarizations are measured in different orientations. Even though the photons are not entangled, the way their states are prepared allows the outcomes to be correlated in ways that cannot be accounted for by classical statistics. The correlations do not reach the maximum strength allowed by entangled states, but they still surpass the classical limit. This kind of correlation is sometimes described as quantum discord, although discord is a broader concept that can also occur in systems that are entangled. Discord captures the idea that there can be non-classical correlations in a quantum system even when there is no entanglement. These correlations can have operational meaning. They can be used for certain quantum information tasks, such as secure communication or improving the efficiency of quantum algorithms. What makes this phenomenon so intriguing is that it forces us to reconsider what exactly is special about entanglement. For decades, entanglement was seen as the defining hallmark of quantum weirdness. It was the feature that separated the quantum world from the classical one most sharply. But quantum non-locality without entanglement shows that there are other resources in quantum systems. Resources that can be tapped even when entanglement is absent. From a theoretical standpoint, this raises deep questions about what we mean by non-local. In the case of entanglement, the non-locality can be traced to the fact that the state of the whole system cannot be factored into separate states for each part. With non-locality without entanglement, the overall state can be factored, but the measurement outcomes still resist explanation by local hidden variables. This suggests that the measurement process itself plays a more active role in creating correlations than we might have assumed. Some physicists interpret this as a sign that quantum mechanics is not just about states, but about the interplay between states and measurements. The same pair of unentangled particles could produce classical-looking results under one set of measurements and non-classical correlations under another. This means that non-locality is not only a property of the system, but also a property of the interaction between the system and the observer. The practical implications are significant. In quantum computing, for example, it may be possible to perform certain tasks more efficiently by using systems that are not entangled, but still have non-classical correlations. These systems can be easier to prepare and maintain than entangled states, which are fragile and prone to decoherence. Similarly, in quantum communication protocols, non-locality without entanglement could be used to share certain types of information securely, without the technical challenges of distributing entangled pairs over long distances. It also has potential relevance to our understanding of quantum thermodynamics and the role of information in physical systems. If non-classical correlations can exist without entanglement, they might contribute to processes such as work extraction, error correction, or even the fundamental limits of measurement precision in ways that we have not yet fully explored. Philosophically, the existence of non-locality without entanglement complicates the tidy narrative that spooky action at a distance comes only from entanglement. It suggests that the quantum world has layers of subtlety beyond the binary distinction of entangled or not entangled. The underlying mathematical structure of quantum mechanics allows for richer relationships between systems than our classical vocabulary can easily express. In the end, quantum non-locality without entanglement is another example of how quantum theory continues to reveal surprises even in areas we thought were well understood. It shows that the boundary between classical and quantum is not drawn in a single place. It is more like a set of overlapping zones, each with its own rules and exceptions. This particular phenomenon occupies one of those in-between zones, where particles are not linked in the strongest possible way, but still behave in a manner that classical reasoning cannot account for. In our everyday experience, time feels like it moves forward no matter what we do. You can pause a movie, you can stop moving for a while, but the clock on the wall will keep ticking, and the world around you will continue to change. In physics, this steady flow of time is something we take for granted in classical systems. Processes evolve continuously according to the rules of motion, and observation does not halt their progress. But in quantum mechanics, there is a strange and counterintuitive effect known as the quantum Zeno effect, which shows that under certain conditions, simply observing a system repeatedly can prevent it from changing at all. In other words, in the quantum world, watching something closely enough can, in a real and measurable sense, freeze its evolution. The quantum Zeno effect is named after Zeno of Elea, an ancient Greek philosopher famous for his paradoxes about motion and change. In one of his most well-known arguments, he claimed that a moving arrow is actually motionless at every instant in time, because at any given instant it occupies a specific position. While Zeno's paradoxes are resolved easily in classical physics using the concept of continuous time and motion, the quantum version is not a philosophical trick. It is a direct result of how quantum systems evolve and how measurements affect them. To understand the effect, start with a basic feature of quantum theory. A quantum system can exist in a superposition of different states, and over time it can evolve from one state to another according to its natural dynamics. For example, an unstable atom in an excited energy state will eventually decay to a lower energy state, emitting a photon in the process. The rules of quantum mechanics allow us to calculate the probability that the atom will still be in the excited state at a given time. If we let the atom evolve undisturbed, this probability will gradually decrease according to an exponential decay law. However, quantum mechanics also tells us that measurement plays a special role. When we measure a quantum system, we cause its wave function to collapse into one of the possible outcomes associated with the measurement. If we measure the atom and find that it is still in the excited state, the act of measurement resets the wave function to that state, effectively starting the decay process over from that point in time. Now, imagine that we measure the atom not once, but very frequently. Each time we check and find it still in the excited state, we collapse its wave function back to that state, giving it no chance to evolve toward the decayed state in between measurements. If the measurements are made rapidly enough, in the theoretical limit, continuously, the system can be held in its initial state indefinitely. This is the quantum Zeno effect, the slowing down or complete halting of quantum evolution due to frequent measurement. The mathematical basis for this lies in the fact that, in quantum mechanics, the probability of a system leaving its initial state increases quadratically with very short timescales. This means that for extremely short intervals, the likelihood of change is very small, and if you keep collapsing the system back into the same state before significant change can occur, the evolution is suppressed. The effect was first proposed theoretically in the 1970s by physicists Baidyanath Misra and George Sudarshan. At the time, it was seen as a curious consequence of the formalism of quantum mechanics, but it was unclear whether it could be demonstrated in a real experiment. In 1990, a team led by Wayne Itano at the National Institute of Standards and Technology, NIST, performed the first clear experimental test. They used a system of trapped beryllium ions prepared in a particular quantum state, which could naturally transition to another state. By applying a sequence of rapid measurements, they were able to suppress these transitions and keep the ions in their initial state far longer than they would have remained without observation. The results matched the predictions of the quantum Zeno effect, confirming that it was not just a mathematical curiosity, but a genuine physical phenomenon. Interestingly, the effect can also work in reverse under certain conditions, producing what is called the quantum anti-Zeno effect. In this case, frequent measurements can actually speed up the transition between states instead of slowing it down. Whether you see the Zeno or anti-Zeno behavior depends on the details of the system and how the measurements interact with its dynamics. This adds another layer of complexity to the relationship between observation and change in the quantum world. From a practical perspective, the quantum Zeno effect has important implications for quantum technology. One of the major challenges in building quantum computers is protecting fragile quantum states from decoherence. the unwanted interaction with the environment that causes superpositions to collapse prematurely. In principle, the Zeno effect could be used to stabilize certain quantum states by monitoring them in a way that prevents them from evolving into unwanted configurations. This would not be as simple as just looking at the system, because any measurement that gathers full information will collapse the state entirely, which is usually not desirable in computation. But carefully designed partial or weak measurements could help preserve coherence for longer times. The effect also appears in contexts outside quantum computing. In nuclear physics, it has been proposed that the decay of unstable particles could be influenced by frequent observations. In optics, photons traveling through certain media can have their absorption suppressed by repeated checks on their presence. In all these cases, the common thread is that the act of probing the system changes the system's evolution, sometimes dramatically. Philosophically, the quantum Zeno effect is another example of how quantum mechanics forces us to rethink the role of the observer. In classical physics, observation can be made passive. You can watch a ball roll down a hill without affecting its motion in any significant way. In the quantum world, there is no such thing as a completely passive observation. Every act of measurement interacts with the system, and if it is done often enough, it can prevent the system from doing what it would naturally do. This leads to interesting questions about the nature of time in quantum mechanics. If a process can be frozen simply by checking on it repeatedly, what does that say about the flow of time for that process? From one perspective, time has not really stopped. The external clock still ticks forward. But from the perspective of the quantum system, its evolution through different states has been halted. The system is effectively trapped in a moment, unable to move forward in its internal timeline because each attempt to do so is interrupted by a measurement that resets the clock. There are also intriguing links between the quantum Zeno effect and some of the other paradoxes we have discussed. In the Elitzur-Weidmann bomb tester, for instance, certain advanced versions use the Zeno effect to dramatically improve the efficiency of interaction-free measurements. By repeatedly checking the state of the photon in a carefully controlled way, these setups can determine the presence of an object without disturbing it, while minimizing the risk of triggering it. In the end, the quantum Zeno effect is a vivid illustration of the central role that measurement plays in quantum physics. It shows that observation is not just a way to gather information. It is an active process that can fundamentally alter the course of events. In our everyday world, you cannot stop a candle from burning down by staring at it. But in the quantum world, you can. If the candle is replaced by a system evolving between quantum states and the staring is replaced by rapid, repeated measurements. In classical physics, time is a one-way street. Causes lead to effects, and those effects can become causes for later events, but never the other way around. A glass falls from a table. It shatters on the floor, and no matter how long you wait, the pieces will not spontaneously reassemble and leap back into your hand. The arrow of time seems fixed, tied to the steady increase of entropy, the measure of disorder in the universe, as described by the second law of thermodynamics. This is the way we experience time in daily life, and it is the foundation for how we intuitively understand events and their sequences. But in the underlying equations of physics, especially in quantum mechanics, the rules do not inherently distinguish between past and future. The fundamental laws are time-symmetric. If you took a film of certain processes at the atomic or subatomic level and played it backward, the reversed sequence would still satisfy the laws of motion. This symmetry suggests that, at least in theory, The equations governing microscopic events do not care about which direction time is flowing. It is only when we scale up to the messy, thermodynamic world of large systems that an arrow of time emerges. This raises a provocative question. If the microscopic rules are time-symmetric, could the future influence the past in the same way the past influences the future? This is the starting point for an interpretation of quantum mechanics known as time-symmetric quantum mechanics, or sometimes the two-state vector formalism. It was developed primarily by Yakir Aharonov, Peter Bergman, and Joel Lebowitz in the 1960s, and it treats quantum events as being determined not just by conditions in the past, but also by conditions in the future. In the standard formulation of quantum mechanics, we describe a system by a wave function that evolves forward in time from some initial condition. At a given moment, we can use this evolving wave function to calculate the probabilities of different outcomes for any measurement we might perform. In the two-state vector formalism, however, the picture is expanded. The state of a system at a given time is described by two wave functions, one that evolves forward from the past and another that evolves backward from the future. These two descriptions meet in the middle, and together they determine the probabilities of what can happen. To see how this works in practice, imagine a simple quantum system such as an electron that can be in one of two states, up or down. In the normal approach, you would prepare the electron in some initial state, let it evolve according to the rules of quantum mechanics, and then measure it at a later time to see whether it is up or down. The two-state vector formalism adds a second step. After making that final measurement, you also consider a wave function that starts at the measurement outcome and runs backward in time toward the preparation moment. The idea is that the complete description of the electron at any intermediate time requires both the forward-evolving wave function from the preparation and the backward-evolving wave function from the result. When you combine these two pieces, certain intermediate measurements can have very different probabilities than you would expect if you only considered the forward evolution from the past. In some cases, the backward-evolving wave function can cancel out certain possibilities or amplify others, leading to unusual predictions. This is especially evident when you use pre-selection and post-selection together. That is, when you choose a specific initial state and a specific final state, and then ask questions about what happens in between. One of the most striking consequences of this approach is that it provides a natural framework for explaining some of the paradoxes we've discussed in earlier chapters, such as the three-box paradox or the quantum Cheshire cat. In these scenarios, the combination of initial and final conditions can produce intermediate situations that seem impossible if you only think in terms of past causes influencing future effects. In the two-state vector picture, these situations are less mysterious because the intermediate state is shaped jointly by the past and the future. For example, in the three-box paradox, the certainty of finding a particle in one box if you look there, and the certainty of finding it in another if you look there instead, can be understood as the result of interference between the forward and backward evolving wave functions. The post-selection, the choice of a specific final state, effectively filters the possible histories in a way that forces the particle to behave differently than it would if only the past mattered. This raises an intriguing philosophical possibility. In some sense, the future is already woven into the present. Of course, this does not mean we can simply choose a desired future and make it happen, because the probabilities are constrained by both the past and the future, and the future itself is not something we can arbitrarily set. But it does mean that the flow of influence in quantum systems might be more symmetric than our usual cause and effect thinking suggests. It is important to note that time-symmetric quantum mechanics does not allow for paradoxical communication into the past. You cannot send a message backward in time to warn yourself about a mistake or to alter an outcome. The framework respects the statistical structure of quantum theory, which preserves causality at the macroscopic level. What changes is not the possibility of signaling into the past, but the way we think about what determines the state of a system at a given time. Instead of being determined solely by the initial conditions, the state is shaped by both what has already happened and what will happen. Some physicists see this as a more complete and elegant way of understanding quantum phenomena. Others are more cautious, noting that while the mathematics of the two-state vector formalism is consistent with standard quantum mechanics, it has not yet been shown to make unique predictions that could distinguish it experimentally. In that sense, it is more of an interpretational framework, a different way of packaging the same predictions, rather than a new theory with different outcomes. Nevertheless, experiments involving weak measurements have provided indirect support for the usefulness of the time-symmetric perspective. Weak measurements, which gently probe a system without fully collapsing its wave function, can reveal average properties of a system between two strong measurements. In some cases, the results of these weak measurements align neatly with the predictions of the two-state vector formalism, suggesting that thinking in terms of forward and backward evolving states can give additional insight into quantum behavior. One of the more speculative ideas inspired by time-symmetric quantum mechanics is that it could offer a new way of thinking about the arrow of time itself. In our macroscopic world, the arrow is tied to entropy, and we see clear asymmetry between past and future. But if the underlying laws are symmetric, perhaps the arrow is not an intrinsic feature of time, but rather an emergent property of the boundary conditions of the universe. The special low-entropy state at the Big Bang and the conditions that will exist in the far future. In this view, both ends of time may play a role in shaping the universe we see today. There is also a connection to certain interpretations of cosmology, where the entire universe is treated as a closed quantum system with both an initial and a final boundary condition. In such models, the large-scale structure and evolution of the cosmos could, in principle, be influenced by both its beginning and its end. This is a radical departure from the standard picture in which the early universe sets the stage and everything unfolds from there, without any influence from the far future. Critics of these ideas point out that we have no empirical access to the final state of the universe, and without that, the two-state vector formalism remains a mathematical curiosity. Supporters counter that even without knowing the final state, the formalism can be applied to subsystems with defined pre- and post-selections, yielding insights into experiments that might otherwise seem puzzling. From a broader perspective, time-symmetric quantum mechanics is part of a long tradition in physics of seeking deeper symmetries. Symmetry has been one of the most powerful guiding principles in theoretical physics, from the conservation laws of energy and momentum to the unification of forces in particle physics. The idea that time might be fundamentally symmetric at the quantum level is a natural extension of this trend. Whether it will ultimately lead to new physics or remain an alternative interpretation is still an open question. For now, the main takeaway is that the division between past and future is not as rigid in quantum mechanics as it is in our everyday thinking. At the microscopic level, the rules are written in a way that allows the future to stand alongside the past in determining what happens now. The loops in time suggested by this picture are not literal causal loops where you can change history, but rather a conceptual loop in which the fabric of events is woven from threads coming from both directions in time. If you step back and consider all the paradoxes we have discussed in this series, from the delayed choice quantum eraser, where a decision in the present appears to influence the past, to the quantum Zeno effect, where observation can halt change. Time-symmetric quantum mechanics offers a unifying way to think about them. In each case, the weirdness is less shocking if you accept that quantum events are not determined solely by their past, but are also constrained by their future. It is a perspective that does not erase the mystery of quantum mechanics, but it does shift the focus. Instead of asking how the present gives rise to the future, you begin to ask how the present is shaped by the dialogue between the two ends of time. It is a dialogue we cannot hear directly, but one whose traces are all around us in the strange and subtle patterns of the quantum world.